Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit number 10, Lesson number 2 on the circumference of a circle. Just like perimeter in the last lesson, this is a topic that should be familiar to you. In fact, we're going to spend about only half the lesson actually using the circumference formula for a circle, which should essentially be review for you. And then we're going to move on and kind of take a look a little bit at where the circumference formula comes from. But first, let's recall what circumference is. Right? The circumference is simply the distance around the outside of a circle, or the length of a line segment that could wrap around the circle. Now, essentially, I've always kind of been a little bit bothered by the term circumference. To me, there is literally no difference between circumference and perimeter, except possibly that circumference is sort of a bent length, if you will, versus perimeter, which is typically reserved for the sum of sort of straight line lengths. But they're really the same. Let's kind of get a little illustration of this really quickly by going over to a GeoGebra applet that's a little bit different, right? Let's take a look at this. Here, I've got a circle, and it's got a diameter of 4, but whatever. Now, keep in mind, right, this red line that goes around it, when I drag the circle along, right, what you can see is that that circumference is unraveling, right? And there it is, kind of drawn out there. Now what's cool is we can think about how the circumference relates to the diameter, or the maximum distance around the circle. And you can kind of see that if I drag this, there's 1 diameter, 2 diameters, 3 diameters, right? So the circumference of a circle is slightly more than 3 of the diameters of the circle. Now I can't drag the thing back. There it goes. But take a look at that one more time. 1, 2, 3. Slightly more than 3 diameters of a circle. And what that does is it brings us to the circumference formula for a circle, right? A formula you've seen before. The circumference of any circle is the number pi times the diameter of the circle. Or, more common in higher level math, the circumference of a circle is 2 times pi times the radius. And that should make sense because, of course, for every diameter, there are 2 radii, right? 2 radii are the same length as any diameter. We're going to use both of these formulas at various points in time, and we may even use this one more often, even though you're probably more used to that one. Keep in mind, of course, that pi as a number, right, is about 3.14, right? So when we saw in that little GeoGebra applet that just slightly more than 3 diameters take up the circumference, that's what we're seeing, right? It's actually 3.1415, etc. diameters that can be wrapped around any given circle. Let's take a look at how that plays out in a problem that you could actually see in Common Core geometry. Exercise number 1. For the circle whose equation is x squared plus y squared equals 25, which of the following is closest to its circumference? Show how you found your answer. All right. Well, why don't you pause the video now and see if you can figure out how this is done. All right. Well, let's take a look. We studied the equations of circles in the coordinate plane in the last unit, unit number 9. And whenever we have a circle of this form, x squared plus y squared equals something, this number, and this is extremely important, is the radius squared, right? So obviously, if the radius squared of a circle is 25, then the radius is the square root of 25, or 5, all right? We can now think to ourselves, well, the diameter therefore is 10, or, if we want to use this formula, or we could use this formula if we just wanted to use the radius instead. I'm gonna stick with this one. It's an important formula to get used to. So the circumference now is 2 times pi times the radius, all right? And of course, in order to really come up with that answer, we may have to use our calculators. So really quick, let's jump out of here, back into our TI. Simple enough, we can hit 2. The pi button is right up here. All right, we can get my pi, 2 times pi times 5, and we end up having our circumference, 31.4. Now again, if you love the pi times diameter, you could have easily said pi times 10, right? And that gives me exactly the same number. Now, of course, that works out that way because multiplication is both commutative and associative, all right? So if we're thinking about 2 pi times the radius, right, well, we could just think about doing 2 times the radius, which is the diameter, and then multiplying by pi instead. Let me just kind of erase those. And let's go back and select the correct answer, 31.4 for choice 3. Again, there's not a lot that's new in this particular part of the lesson. I mean, sure, we had to recall this business from the last unit, but ultimately speaking, using these two formulas, circumference equals pi times diameter, or circumference equals 2 pi times radius, is just a sort of plug and chug routine, if you will. Anyway, let me step out of the way for a moment, take a look at what you need to, and then let's move on to the next problem. All right, let's do it. Okay, let's take a look at exercise number 2. A tree trunk has a roughly circular cross-section. A logger uses a tape measure to find that the circumference of the cross-section is 6 feet long. Which of the following would be the best estimate of the diameter of the cross-section? So keep in mind, you know, what's going on here. You know, I've got my tree, and we've got somebody who comes in and says, all right, well, I've got a cross-section that's essentially circular, right? And what I kind of want to know is what's the diameter of this tree? Well, it's very easy to take my tape measure out, a bendable tape measure, put that, string it around, and what I find, right, is that the circumference of the cross-section is 6 feet long. We know the circumference is 6 feet. What we want to try to figure out is what the diameter is. Pause the video now and see if you can figure out what the diameter is, or which one of these is closest to the diameter. All right, now one thing to note, all of these answers are in inches, right? And yet the circumference has been given in terms of feet. So it may be wise to convert those feet into inches. In fact, if I come over here so I have a little bit more room, I could say the circumference is 6 feet times 12 inches per feet, or per foot, as the case really is. So the circumference is 72 inches. Now, we know that the circumference is pi times the diameter. And we know that is 72 inches. So in order to figure out the diameter, all we have to do now is divide both sides of this equation by the number pi, right? And then we need to use our calculator. So let's jump back into it. Let me clear this out. I'm going to do 72 divided by pi. And there's our diameter, 22.918 inches. Let's go back into it. Looks like that's pretty close to 23 inches. Choice 2. Or at least that was supposed to be a 2. All right? 23 inches. It was 22.9, etc. over there on the calculator, but the closest one is 23. All right? Take a look, copy down anything you need to, and then let's keep moving on. All right, let's do it. Now, it is very common that you'll see problems in geometry and in the real world that both combine circles and straight line segments, as we have here. Let's take a look at what this problem is asking us to do. A garden is to be enclosed by a combination of a rectangle and a semicircle. Fencing is to be put up around this garden, but not along the dashed line. How many feet of fencing would be needed, round to the nearest foot? All right, so here we've got this sort of like 3 sides of a rectangle, and at the end of that rectangle, we've got a semicircle. And I want to know how many feet of fencing I need to go around this entire thing. Pause the video now and see if you can work through this. All right, well, there's 2 portions really of this perimeter, if you want to call it that, right? There's the portion that consists of the straight line segments. Maybe I'll call that P1 for first perimeter, right? And what would that be? Let's see if we can get rid of the red. That would be that 17 feet plus 12 feet plus another 17 feet. But again, note, not an additional 12 there. That is not on the outside of the figure, right? So that's easy enough. That's going to be 34, 44, 46 feet, right? And that's just the portion of the perimeter that goes around the rectangle. Now we need to find the portion that goes around the semicircle. Now obviously, the circumference of a circle, right, is pi times its diameter. But this is only half of a circle. So we either need to throw out a multiplier of 1/2 or we need to divide by 2. Of course, those all have the same thing. Maybe I'll call that P2 for the second perimeter. And that would be 1/2 of pi times the diameter. Now, hopefully it's pretty obvious that the diameter of the semicircle, right, is going to be the same as that 12-foot length. So it's just this. Now, if you wanted to, you could multiply the 1/2 by 12 and say, well, that's just going to be 6 times pi. Okay. Or you could leave it like this. It's kind of up to you. Ultimately speaking, we need how many feet are going to be going around this to the nearest foot. So we need to have that P1 plus P2, right? That 46 plus the 6 pi. So let's take a look at that. 46 plus 6 times pi. And that's going to be 64.849, etc., right? Rounded to the nearest foot, 65 feet. Let me put the 64.8 up there for now. And then that, rounded to the nearest foot, is 65 feet. All right, should be simple enough. Go ahead and write down anything you need, and then we're going to look a little bit more deeply at the circumference formula of a circle. All right, let's keep going. Now, to truly appreciate the circumference formula of a circle, and many formulas that we're going to see in this unit, you really have to have calculus. There's no getting around it. And calculus is quite a few levels above where we're at now. You know, we're in geometry now. Typically, the next course you would take would be Algebra 2. The course after that would be sort of pre-calculus, and then after that would be calculus, okay? But we can at least explore it a little bit by looking at regular polygons and what their perimeters are, and this is kind of cool. So let's take a look at exercise number 4. The picture below shows regular polygons whose length from center to any vertex is staying a constant 1 inch, okay, 1 inch. As the number of sides increases, what should the perimeter of the regular polygons approach, and why? I want you to think about this a little bit, okay? What should these perimeters get closer and closer to? Well, they should get closer and closer to the circumference of a circle whose radius is 1, or whose diameter is 2, right? And that, I hope, is very obvious. In fact, if you were to stand way back away from here and look at this 15-sided, figure, regular polygon, it probably looks more or less like a circle. And the more sides there are, the more it will look like a circle, because the larger these interior angles become, right? So in fact, it should approach 2 pi times the radius, or 2 pi times 1. In fact, let's get that accurate to some decimal accuracy here. Let me just go into this really quick. So 2 times pi, I guess times 1, we don't really need that in there. But 6.2831, etc., because pi is an irrational number, this is also an irrational number. It gets truncated eventually here. Maybe I'll just write out 6.283. 6.283. Right? And that is because the shapes are getting closer to a circle. Now, let's see if we can see that number 6.283 by working with right triangle trigonometry and regular polygons. All right, first, let's go with a 10-sided figure. Exercise 5, let's take a look. It says, shown below is the regular 10-sided figure from above, along with a related isosceles triangle. Determine the perimeter of the decagon. Round your answer to the nearest hundredth. All right, so here we go. Here we've got a decagon, a regular decagon, 10-sided figure. Here we've got that distance from the center out to any vertex being equal to 1. And I want to figure out what the perimeter of that decagon is. Now, I did something very, very similar to this, or we did something very, very similar to this in the last lesson when we figured out what the perimeter of a pentagon was, whose distance, I think, from the center out here was 5 or something like that. Doesn't matter. What I'd like you to do is pause the video now and see if you can figure out what the perimeter of that decagon is. You're going to have to use right triangle trigonometry in order to do it. All right, well, let's take a look. So first things first, right? The idea here is that we could take this decagon and we could slice it up into 10 sort of slices like this, all of which are absolutely identical to this one over here. Now, key is, though, that those 10 slices are not right triangles. They're isosceles triangles, but they're not right triangles, okay? In order to get a right triangle, we actually have to slice them in half like this. Now, what do we know? Well, we know that this entire angle here is going to be 360 degrees divided by 10, or 36 degrees. But ultimately, what we really want is we want this angle right in here. Okay, this little guy. But that's going to be 36 degrees divided by 2, or 18 degrees. Now, why do we want that? Well, we want it because if I now take that little right triangle, and I'm going to kind of flip it on its side like this. Okay, remember its hypotenuse is 1. This thing is 18 degrees. Okay, I can now figure out what the length of this side is. And I'll give it an x right there. Because I've got that acute angle, I've got the hypotenuse, and I've got x, I can now use right triangle trigonometry and say, well, that's the opposite side. That's the hypotenuse. And that's going to be the sine ratio. I can say the sine of 18 degrees is equal to x over 1. So x is just 1 times the sine of 18 degrees. Better yet, x is just the sine of 18 degrees. Because, of course, 1 times anything is just that thing. Now, that's simply what this length is right here. But that, of course, means that the length of any given side of this decagon is 2x, right? Or 2 times the sine of 18 degrees. But how many of them are there? Well, there's 10 of them, right? So that means I've really got 20x, yes? For each one of these, I had 2, 4, 6, 8, 10, etc., right? So ultimately, the perimeter is going to be 20 times x, which is 20 times the sine of 18 degrees. And let's take a look at what that is. Clear. 20 times the sine of 18 degrees. Oh, should probably make sure I'm in the right mode. Let's take a look. There I am, degree mode on my calculator. If I'm in radian mode, completely incorrect answer. But I've got 20 times sine 18, and I get 6.180. That's my perimeter. 6.180. Now, what did they want? Round to the nearest hundredth. So I can just say 6.18. Now, before we move on and continue, right, remember, I'm thinking that as I increase the number of side lengths, I'm going to get closer and closer to the circumference of a circle whose radius is equal to 1. And remember, I calculated that as 6.283. With 10 sides, I'm already at 6.18. Not too far off from this. In fact, only about 1/10 off of the circumference of a circle with the same radius. All right? So now, let's make this a little more abstract. Look at something that probably looks like a terrifying formula, but then see where it comes from. Let's take a look. Exercise number 6. Show that the perimeter of any of these regular polygons with a distance from the center to the vertex of 1 is given by, look at this formula. P equals 2n sine of 360 divided by 2n, where n is the number of sides. Well, just for a minute, right, you can kind of test that with the one that we just had, right? The one that we just had, n was equal to 10, right? And if I took that 10 and I kind of plugged it into the formula, right, what I'd get is I'd get 2 times 10 times the sine of 360 divided by 2 times n, which is 20. And that would be 20 times the sine of 18. All right. And that's, in fact, exactly what we had. You can see it right up here. All right. But why does this formula give us the perimeter no matter what the value of n is? Well, let's kind of go through the process exactly like we did up here, but instead of using the 10 right here, let's just use n, right? So same idea, right? If we took one of these things and we broke it into these slices, these isosceles triangle slices, right? Now what would we know? All right, remember it's got n sides. So we would know that this angle right here would be 360 degrees divided by n, right? We would know that. Now, keep in mind, though, that what we would really want, right, is we'd really want this angle here, which would be 1/2 of this, right? So we would have 1/2 of 360, whoops, that's not quite right, 1/2 of 360 divided by n, which would be 360 divided by 2n, all right? Now, that then gives us this little right triangle that we were looking at before, right? The difference is before, with the 10-sided figure, we had that angle in there as 18 degrees. Now it's this ugly, ugly thing, this 360 divided by 2n. If we call this x, though, just like we did before, then we could say, well, all right, we've got the sine of 360 divided by 2n is equal to x, the side opposite, divided by the hypotenuse, 1, which would then obviously tell us that x was just equal to the sine of 360 divided by 2n. Okay, and again, think, this is exactly what we did when n was equal to 10, right? We just knew n was equal to 10. Now, keep in mind, though, that the entire side length would be 2x, right? And how many of those would we have? Well, it's an n-sided figure, so we'd have n of them, right? So we would have the entire perimeter would be n of these things that are 2x, and that would be n times 2 times the sine of 360 divided by 2n. And just to make it look like what we were looking to do, I think I'll just flip-flop this multiplication, n times 2, and make it 2 times n. And we find that the perimeter is 2 times n times the sine of 360 divided by 2n. All right. Oh, Mr. Weiler, is this a formula we have to memorize? No, not particularly. No, not at all. You know, what we're really trying to look at here is how, when you increase the number of sides of regular polygons, their perimeters get closer and closer to the perimeter of a circle, or the circumference of a circle. And now we'll really see it. Remember, right, we think that as the number of sides gets larger, the circumference should get very close to the perimeter should get very close to the circumference of this circle. And what I'd like to do now is see what this thing looks like when I've got 5 sides, 10 sides, 50 sides, 100 sides, 200 sides. Okay, so for this, I definitely have to go over to the calculator. All right, so let's do it. Let's come into the calculator. And one convenient way of doing this is to go into my y equals. Okay, now in this, I'd love to put the n in, but I'm going to actually use x instead. Now remember, the formula was 2n, so excuse me, I'm going to do 2x times the sine of 360 divided by, now it's a little bit tricky, 2x, all right, like that. So this is the formula that we had before, but instead of n, we have the variable x. And what I'm going to do is I'm now going to go into a table, all right, and I'm going to actually go over to the independent variable and tell it to ask me what I want, okay? And now I'm going to pop into my table. Okay, so what did I want? I wanted to know what the perimeter would be if I had 5 sides. And that perimeter would be 5.8779. Let me throw that in. Let me extend the page a little bit. Okay, let me go back to my calculator. I wanted to know what the perimeter would be if I had 10 sides. 6.1803, which is exactly what I got for that decagon, 6.1803. Whoops. There it is, 6.1803. Now let's really make the number of sides large. Let's go with 50. See what happens there. 6.2791. Remember, I would expect these things to get closer and closer to 6.283. With 50 sides, I'm now at 6.279, right? Getting very close. What was it? I wanted 100 sides now. I bet if we had a 100-sided polygon, it would be hard to even tell the difference between it and a circle. Now we're at 6.2822. Again, we're supposed to be getting closer and closer to 6.283. We're now at 6.282. And now let's go with 200 sides. We could keep doing this. We could go with 10,000 sides if we wanted to. Then it would be very close. 6.2829 or 6.283. Let's just round it to that. And in fact, what we see with that, it is essentially the circumference of that circle. All right? And notice, nowhere in any of these calculations, in this calculation or in any of these calculations, is the number pi actually sitting there. And yet, that number, 6.283, is roughly 2 times pi. And we're kind of seeing the pi now jump out at us through the use of right triangle trigonometry. Now again, lots of students might be kind of worried, oh my gosh, do I have to derive this formula on the Regents exam? Do I have to go through this? Probably not. The 2 things you should take away from this is, number 1, you should be able to do something like this. You should be able to calculate the perimeter of a regular polygon using right triangle trigonometry if you know the distance from the center out to any one of the vertices. So number 1, you should be able to do that. Number 2, right, you should also know that if you for some reason needed to approximate the perimeter of a regular polygon with a lot of sides, you could always use the circumference formula of the circle to get a very good approximation, especially when the number of sides is quite large. All right, let's move on. Let's wrap this thing up. Got to go back to full screen in order to do that. So today what we did is we reviewed the circumference formula for a circle, and we used it in a variety of applied problems. And most of the homework you're going to see concerns that. The second half of the lesson, of course, we were kind of looking at this more sophisticated viewing of the circumference formula and where the number pi comes from. And again, pi is quite a mystery. It took literally thousands of years for people to really get a good feeling for it, to really understand how to calculate its decimal accuracy to any given level they want. And we have barely brushed the surface here by looking at that last set of exercises involving right triangle trig. All right, don't be too overly concerned about that. It's important that you see it. It's important that you understand how the circumference of a circle relates to the perimeter of regular polygons. But as long as you kind of got the general gist, you're probably okay. I want to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.